Hello guys, in this video we are going to find out the time period of rotation. We will establish a relation between time period of rotation of satellite and the radius of orbit. Okay, now we have the force of gravitation, okay, that is Gmm upon r square. So that is what we know. Okay, and this r is nothing but radius of earth plus height at which the satellite is orbiting. Now what is the velocity? Velocity is root over g m upon r, right? Now what is the centripetal force which is which is necessary for the circular motion? Now that is mv square upon r, that is the centripetal force Fc. And now this centripetal force has to be equal to the gravitational force of attraction, correct? So now let us put this mv square upon r is equal to this, we'll just equate that. So mv square upon r is equal to g m upon r square. Now what is my velocity? Velocity is distance upon time. So what is the distance? The time period is time taken to complete one complete circle, correct? And in while it executes one complete circle, the distance traveled is equal to the circumference of the circle, and it is nothing but 2 pi into r, and time taken is the time period, and that is your velocity here. So in place of this v square I am going to put this, correct? This r I'll cancel over here with this square sign. So my velocity square, that would be equal to 4 pi square r square, and that is upon t square, correct? And that is equal to gm upon r. Now I'm going to take this t square on that side, this r on this side, and gm down there. So my t square is going to be equal to 4 pi square upon gm into r cube. Now here my 4 pi square is a constant, universal gravitational constant is obviously a constant, and mass of earth, it is again constant. So I can say that t square is proportional to r cube, or then I can say that t square is proportional to r plus h cube. So that means my period of rotation, it will depend on the height. Again, my capital R radius of earth is constant. So as my h varies, my t varies. Greater the h, greater will be the period of rotation. This is one important result, and we would find this in Kepler's laws as well. So now let us understand what is Kepler's laws. Okay, there are three laws put forth by Kepler. Now the first law is, it is the law of orbit. Now formal statement of this law of orbits is, every planet revolves around the sun in an elliptical orbit, with sun situated at one of the principal foci of the ellipse. Right? That is one thing. So now that means if this is the elliptical orbit, then and I have these two principal foci of the ellipse, then sun will be situated somewhere here and the planet is here, correct? That is law of orbits. Now second one is law of equal areas. Now statement of law of equal areas is, in equal time intervals, the area swept by the position vector drawn from the planet to sun is same. Now let me explain this. For example, my planet is at position A here. Okay, in let us say 30 days it reaches this point B here. Correct. Now what I do, I connect this, I draw this radius vector from the sun to the position of the planet, initial position of the planet, and then another radius vector with the next position of the planet. Correct. Now time taken for traveling from A to B is, let us say, 30 days. Okay. Now let us take any other position of the planet. Let us say we'll take this position C here and position D here. Okay. And now again I'll draw position vectors here or radius vectors here. So now again from point C to point D, what is the time taken? Again it is 30 days. Okay, so A to B is 30 days and C to D is also 30 days, and this law states that this area and this area, these areas are equal. Now there is one very important conclusion that we can draw from here. That means when the planet is closer to Sun, it travels faster. Its linear velocity is more. When it is away from Sun, the linear velocity is less, and that is quite obvious, right? As the distance between the two masses increases, the centripetal force decreases, and then if the centripetal force has to decrease, then mv square upon r has to be smaller. That means the velocity has to be smaller. Correct. So it works with what we have stated earlier. Now the third law is law of period. And Keppler said that the square of the time period is proportional to the cube of radius of orbit. So he said that t square is proportional to r cube. And is it not something which we found here? So we have already proved that yes, that is that is a fact. You know, if you put all these things together here, we are getting the same thing. So that was about Kepler's three laws. In the next video, we are going to talk about weightlessness in a satellite.